Hi everyone, my name is Xiaolin. Today I'll be present the predictive models for the customer churn data. In this sections, I will provide a quick overview of the data I use. I found my data set from Gaggle and I imported into R using the public link I generated through GitHub. And this data has about 10,000 customer with 14 features. They are generally about customer account profile, banking status, and their demographic information. Specifically, how many years they've been with the bank, whether they have the credit card, and how many credit score they have, and where they're from, their age, and estimate income. And the target variable is exit. It tells whether a customer stay with the bank or not. As we can tell, it's a binary classifications problem where 0 means customer stay and 1 means exit. And the goal of this project is to build a strong model that can predict whether a customer is likely to leave or not. To do this, I will identify the key variables that influence the predictions, and I would test several different models and compare their performance using the F1 score. It is very helpful for imbalanced data set, as well as select the best models. And why this is important, because it can help the business understand exactly which specific customer is at risk of churning. And for the data explorations, I create a statistical summary to see the overall range and the typical values for each feature. And for the numeric features, I use histogram to check their distributions and backspot to check their outlier. And as a result, the skew distributions are credit score, age, and balance. And when we're comparing by classes, the outlier are most likely appear for the class who stay, and it shows in a credit score, age, and number of product. Similar approach to the category features, but I use bar graph to visualize them. Most of the customers are from France, and they are more male customer than female. And for class differences, customer who stay shows larger difference across category, and those who left shows much smaller difference. For the data transformations, I create a functions to apply a log transformations to all the numeric columns using the log x plus 1 to handle 0. This could improve the skewness of the distribution. And to identify missing values, I use ISNA function to count the numbers of missing value for each column. As a result, there is no missing value I found in the dataset. To detect outlier, I create an outlier function using z-score method, where I calculate the mean, standard deviations to find the z-score, and anything that is above or below 3 considered as an outlier. And after that, I combine the result into a table, and there is 133 outlier for age, 60 for number of products, and 8 for credit score. And to decide whether I should remove this outlier, I also use the z-score method to list all the outlier out. And as a result, they do not indicate any errors, because it is possible to have this in real life. For example, it is possible to have someone who is age between 61 to 90 and could have like a low or high credit score, as well as for the number of product. Because some algorithms work better with standardized data while others do not, I prepared two versions of dataset. One is the normalizing data using the z-score standard deviation, and along with the frequency encoding for categorical feature, and other is only applied to the encoding. Since I went over the z-score method before, then I will move on to my approach to encoding. So for each categorical columns, I create a frequency table and convert the counts to the proportion, and store this as a new encoded columns. After encoding, I remove the original columns to avoid confusions. As you can see, only the geography and the genders are changed, while others stay the same for non-normalized dataset. And for the normalized dataset, it is completely different. I use a heat map to visualize the relationship between variables, where the darker color indicate the stronger correlations. As a result, all the correlations are generally weakly correlated, and meaning that there's no multi-collinearity, and this is very important because high correlations between predictors can make it really hard to interpret their effect and reduce the model effectiveness. Next, I will explain the three models I choose for this data set. The first one is the logistic regressions. It is suitable for the binary classifications problem, and it requires encoded categorical data and ensure no high correlations between the predictors and large sample size and no extreme outlier. The second one is the random forest. It works well with both numeric and categorical features, and then very flexible with different types of data. The last one is gradient boosting machine. It is also very flexible as it doesn't have a strict assumptions about data. For the logistic regression model, I start by training a model using all the predictors on the normalized data set as one of the model requirement. And I then apply a backward stepwise eliminations to remove all the not important features. And as a result, the important predictors are credit score, age, balance, whether if is active members, the geography, and as well as their gender. And to ensure the model was not overfitting, I used a tenfold cross validations, which is splitting the data into 10 parts and rotating the training and testing data set to produce more reliable result. And to evaluate the logistic model, I predict the probability that each customer who end up living in the trained model, I use 0.5 as a cutoff, and the customer with a probability greater than 0.5 identify as no, and less than 0.5 are yes. I define the performance matrix here using the accuracy, true negative rate, positions, recall, and F1 score to see how we perform. And as a result, the model correctly classified 74% of the cases and correctly identified about 60% of the negative cases and about 68 for the positive cases. And the F1 is 82%, which means a good balance between positions and recall. For the random forest model, I also use the k-fold cross validations I create for the logistic model. And here, the use of the expanded grip here is to provide more options for the model to find the best parameter. It determines the numbers of the features that model have for each split. And since small changes in parameter will lead to different result, finding the best one could reach to the highest values in the performance matrix. As a result, the best parameter in this model is 2. Once I have this, I can train my model with the value 2 for parameter, and then I use the same evaluations method as the logistic model. As a result, the turn-in random forest model correctly classified about 86% of the cases and about 96% of the customer who left and 46% of those who stay. And when you compare to the logistic model for F1 score, it has much higher performances, which also mean much effective in identify different classes. Bagging is built into random forest where each tree is trained on the random bootstrap sample of the data, and this help reduce the error, helps preventing overfitting, making the models more robust. For the gradient boost machine model, I also use the tenfold cross validations, and similar to the random forest model approach, I also use the expanded grip function to provide more options for model to find the best parameter. But in this case, it has 4 different elements. It has number of tree and how complex the tree is and how fast the machine learn. And the lower rate usually would produce more effective performance, and as well as the minimum total weight needed in each doe. Once I run that range, And it shows me that the best parameter for this model is when number of trees 500 and 5 for interaction depth and 0.5 for the machine learning rate and at least 10 for total weight needed in each row. The backing for a gradient boosting model, I use the bag fractions equals 0.5. It means that each tree is trained on 50% of the data and helps reduce the overfitting and make it easier to generalize in the model prediction. And I plug this number into the turn model and use it for the evaluation to see how effective it is. As a result, the tune model correctly classified 86% of the case and 52%, about 53% of the negative case and 94% for the positive case. And although it is slightly lower than the random forest rate, it is still showing that a very strong performance for the predicting the turn. To put all the model performance in a summary, random forest has the highest overall accuracy and very effective in identifying customers who are likely to leave, and also has the highest F1 score and the true positive rate. And next, the Guardian boosting performs almost as well as the random forest, but it is slightly lower than the random forest. For the logistic regression model, it has the lowest overall accuracy rate, less effective at identifying for those who left. However, it performs better at identifying those who stay. I split the data into 80% training and 20% for testing because it provides enough examples for the models to learn patterns. After splitting, I use the smoke techniques to over-example the minority class in the training data set. And as we can see, before the original dataset has 80% for class 0 and 20% for class 1. And now we have 50% for the state customer and 44% for those who left. It is much more balanced and provide less biased result. And throughout the model trainings, I use the cross validations to find the high parameter training to improve the overall performance. And in this case, we will use the F1s as the critical matrix to evaluate model because it is very helpful for imbalanced data set or slightly imbalanced, as well as the and finally, I will use F1 score as the most critical performance method since it balances the precisions and recall for predicting churn effectively and very helpful for imbalanced class dataset. How I build the ensemble model is that I combined all three models using the majority voting, which helps reduce the error from each models and provide a more reliable prediction. And in the weight approach, I give higher weights to random forest and the gradient boosting because they are generally stronger and better at capturing complicated data. And logistic model would have the lower weight since it has more restriction. Since our main goal is to predict customers who are likely to leave, random forest is the best model that has highest overall accuracy, recall, and F1 score. And the ensemble model comes in second. However, it's still considered as a very effective model. For the key lessons I learned from this project, after building all three models and the ensemble model, I learned that logics model can handle imbalanced data set, but the predictions tend to be biased toward the majority class. And in the same time, random forest model is very effective at handling imbalanced data set, perform well across almost all the performance matrix. And for the gradient boosting machine, it performed better on imbalanced data set after the hyperparameter training. And lastly, for the ensemble model, I realized that after although combining all the model probability and assigning weights based on their effectiveness can improve overall performance. But however, if there's a weak model curve, it would slightly decrease the prediction accuracy.